All right, let's start going through the spell work. Looking at number 1, at this probability tree. Anytime you are at one of these points right here, you have to choose to travel along one of those two paths. So what they're telling us in this diagram right here is that the probability of choosing this top path is 0.2. What would that be as a percentage? What is 0.2 as a percent? 20%. So there's a 20% chance we travel along this way. So what's the chance we went the other way? 80%. 80%. So the probability of B would be 0.80 or 80%. The way we find the probabilities at the ends here is that we multiply along these branches. So if we chose this top path, there was a 20% chance that we chose this path. And then at this fork in the road, there was a 40% chance we chose the top path. If you multiply 0.20 with 0.40, that's where this 0.08 is coming from. So we still need to find C and D. You guys told me that the probability that we take this first top path is what? What's the probability that we travel this path? 20% right here. So for C, I know I'm going to need to multiply 20% with whatever the probability is of this path. How do I find the probability of this? Standing right here, I have to make a decision, and I'm either going to go this way or this way. What's the chance we went this way? 40%. So what's the chance we chose the other way? 60%. This one down here would be 0.60 or 60%. So if we chose that path, we're going to multiply the 20% that we chose the top path with the 60% that we chose the bottom right there. What do you get on your calculators when you multiply 0.20 with 0.60? 0.12. So a 12% chance. This guy up here, this is the same as 8%. We still need to find what? What are we still looking for? D. We need this one. Back here is where I have to start making decisions. Anytime there's a split in the road, I have to choose one of those two paths. Would I choose the upper path or the lower path at this first decision point if I want to make it to D? Lower. So I have to travel along here. What did we say the chance was that we took this path? 80%. So I'm going to need to multiply 0.80. And then at this point right here, we have to make a decision of either going up or going down. Which one of those will get me to D? Going down gets me to D? I want to go up here. So first decision, I went down. Second decision, I take the top branch. What's the probability there? 70%. Tell me how you got that. Yes, 30% plus 70% gives me 100%. And the chance that we took this bottom path here was 30%. So the top has to be 70%. Let me find a color I haven't used yet. So this one up here is 0.70 or 70%. And we're traveling along this path. So now I need to multiply those together to find out the probability for D. What do you get when you multiply 0.80 and 0.70 on your calculator? 0.56. What is that as a percentage? 56%. And this bottom one, this 0.24, what is that as a percent? 24%. What do you get if you add up 8%, 12%, 56%, and 24%? 100%. All of these n's together, this is saying like if you add all of those up, there's a 100% chance that you end up at one of these four n's. Because you had to make a choice here, and then at the end of each of those branches, you had to make a choice again. Does it add up? Awesome. Thank you for verifying that, Chris. All right, let's go look at number 2. Marco's Pizza offers 10 different pizza toppings and 3 different types of crust. They have hand-tossed, thin crust, and deep dish. I'm a deep dish person myself. I don't like thin crust pizza. I think it tastes like pizza on a cracker. Like, I want to be able to sink my teeth into my pizza. I don't want it to crunch. But that's just me. My husband loves thin crust pizza. He doesn't want to eat pizza and breadsticks at the same time. That's how he describes a deep dish pizza. He's like, I don't want that. I want the toppings. So at our house, we either get 2 different pizzas, or we both get to be unhappy with hand-tossed. But to him and I, a one-topping pizza that's deep dish is different than the same one topping. Like a deep dish pepperoni pizza is different than a thin crust pepperoni pizza. Those are 2 different pizzas in our world. I want to know how many different one-topping pizzas are available here. How many hand-tossed pizzas with 1 topping could you get here? 10. How many one-topping deep dish pizzas could you get? 10. What about thin crust? So how many one-topping pizzas total are available? 30. We look at all of the possible toppings. They had 10 choices for toppings. They had 3 choices for the crust. And we can arrive at that same output of 30 different one-topping pizzas by multiplying all the options for the toppings with all the options for the crust. So there are 30 different one-topping pizzas. All right. We're going to cover the very last thing that we need to touch on in probability today. It's called the concept of independence. We're going to go to page 258 for this. Independent events are events that have no influence over each other whatsoever. Absolutely no influence over each other. An example of 2 events that are independent. There's some paper. An example of events that are independent. My choice of what color shirt to wear today, and the weather in Shanghai, China. These 2 things have absolutely no influence over each other whatsoever. An example of 2 events that are not independent. Whether or not I choose to bring an umbrella with me to school, and what the forecast says the weather is supposed to be like that day. I'm going to look at the forecast, and if it says that there's a 2% chance of rain, it's supposed to be sunny all day, I'm probably not going to grab my umbrella. If it says there's a 90% chance of rain, I'm going to take my umbrella. So information about that first event or the chances of that event influence my decision. Those would be things that are not independent. Independent means no relationship whatsoever. So writing down this definition, what are independent events? This is when the probability of one event in no way influences the probability of a second event. We have a test for this because there are certain things that just in our everyday lives, we might assume these two things have a relationship. It just seems to make sense. It feels like common sense. But when we test it, when we record data about it and we test it, it turns out that these two things actually don't have anything to do with each other at all. What we have observed is a coincidence. There's other situations where we think two things are absolutely not related. That's ridiculous. Why would you ever think these two have a connection with each other? But when we collect data and we analyze that data, it turns out that one actually does influence the other. So we have this test to kind of get around our own cognitive biases here so that we can find relationships that do exist and we can eliminate relationships that don't actually exist. The way we test for independence. If the probability of event A and event B, remember this right here is our and, our intersection. So if the probability of both events happening is exactly the same as the probability of event A multiplied by the probability of event B, then the events are independent. So if they're equal, they're independent. If they're not equal, they are not independent. So what we find, stated another way, equal means independent. And if they're independent, then there is no relationship. If you are an independent person, there is not a relationship happening in your world. If they are not equal, then it means that they are not independent. Which means there is a relationship. These two things are somehow connected to each other. One is influencing the other. I might not know which way that influence is going, and I might not understand why, but I can see that there's some kind of influence happening here. We are going to do several tests for independence to practice with this. So if you look down at number 3, it describes here a situation where we've got a bag of marbles. The marbles in this bag have multiple different colors. And what else have they described? It's not just different colors, but it's also different sizes. So we've got regular sized marbles, and then there's also some really large marbles in this bag. So not a normal sized marble at all. In this bag of marbles, the chance that you reach in and you get a purple marble. What's the chance that you reach into the bag and you grab a purple marble? What do they tell us? 0.4 or 40%. The chance that you reach into this bag and you grab one of the big marbles, regardless of color, is what? 55. So more than half the marbles in this bag are that large-sized marble. The probability that when you reach into this bag, you manage to grab a big purple marble. So it is both purple and big. What's the chance that when you reach into this bag, you get a big purple marble? 0.3, yes, 30%. I want to know whether or not these events are independent of each other. So to test for that, we wrote before that the probability of A and B occurring, if that is equal to the probability of event A multiplied by the probability of event B, then these things are independent and there is no relationship. So what are the events that we're looking at here? 0.4 and 0.55. The 0.4 is for which event? Purple. So the probability of a purple marble, 0.4. And we're going to multiply that to the probability of our other event. What's our other event? Big marbles. The probability of a big marble is what? 0.55. I want to test to see if that is equal to the probability that we grabbed a big purple marble. So it's both big and purple. What did we say the probability of that was? 0.3 or 30%. So you're going to need to grab your calculators now. You're going to need to multiply these two decimals together, the 0.4 and the 0.55. And what do you get when you multiply 0.4 with 0.55? 0.22. Is that equal to 0.3? No. What does that mean about this situation then? Not independent. If they are not independent, does that mean there is or is not a relationship here? There is a relationship. Think about it. If you are independent, you don't have any other person that you need to check with. You are not in a relationship. You are independent. If you are not independent, you got to check with somebody else. You're in a relationship. You can't just make all these decisions without talking to the other person. So if it is not independent, there is a relationship. All right, let's go look at number 4. The probability that it rains on Monday is 0.4, or 40%. Probability that it rains on Tuesday is 0.2, or 20%. Probability that it rains both Monday and Tuesday is 0.08, or 8%. And I want to know whether or not these are independent. So the probability of A and B, if it is equal to the probability of A times the probability of B, then they're independent. What are the events that we're looking at here? Monday and Tuesday, rain on both days. So the probability that it rains on Monday and on Tuesday is what? 0.08, or 8%. What's the probability that it rains on Monday? 40%, or 0.40. What's the probability that it rains on Tuesday? You said point what? 0.2, 0.20, 20%. So grab your calculators for me. We're going to multiply 0.40 and 0.20 together. .08. Is that equal to what we had on the other side? Yes. So these really are equal to each other. What does that mean? They are independent. So does that mean relationship or no relationship? No relationship. Number 5. They don't give me decimals on number 5. What have they given us instead? Fractions. Well, we have that the probability of A and B is equal to the probability of A times the probability of B. Do we have a fraction for this one? Do we have a fraction for the probability of A and B? What is that fraction? 1 over 25, so I'm going to substitute that in. I want to know whether or not that is equal to the probability of A. What's our probability for that one? 2 over 5 times the probability for B. 1 over 4. How do we multiply fractions together? Straight across. So I'm going to multiply the 2 and the 1, the 5 and the 4. What do I get when I do that? 5 times 4 is 20. 2 times 1 is 2. So I end up with 2 over 20. Can I reduce 2 over 20 at all to make comparing easier? What does 2 over 20 reduce to? 1 over 10. Is 1 over 25 the same as 1 over 10? No. So what does that mean then? They are not independent. So if two things are not independent, is there a relationship or not? There is a relationship. If they are not independent, there is a relationship. Number 6, the wording is a little bit tricky. What are we talking about on number 6? A math test. Anything else? Also a chemistry test. What do they tell us about the math test? The probability is 0.75 that what happens? That you do not get an A on your math test. So if I was going to use probability notation, I would say probability of not A on math is equal to 0.75. So let's think on the bright side. It's 0.75 that you don't get an A. So what's the probability that you do get an A? 25%. And you said we're also looking at a chemistry test here. What's the probability that you get an A on your chemistry test? 30%. 0.3. What's the probability that you get an A on both tests? 7.5%. So probability of an A on both tests, 0.075. We want to know whether or not these events have any influence over each other whatsoever. So the probability of A and B, if that is equal to the probability of A multiplied by the probability of B, they're independent and they don't influence each other at all. There's no relationship here. What is this in our example? The probability of A and B. How would I describe that in this situation about the math test and the chemistry test? Yes, getting an A on both. And that probability we wrote down as 0.075. Is that equal to the probability of A? What would we have on this or for this one? 25%. The probability of A on our math test, which we said was a 25% chance, so 0.25. Multiplied by what? 30%. The probability that you get an A on your chemistry test. So we're going to multiply those two together. And what did you discover? It's the same number. So what does that mean? There's no relationship. They are independent of each other. Independent. All right, there's one more on this page. Let's look down at the bottom. Your page, mine has a little bit of a typo on it. Yours doesn't have that symbol. What does yours have in between these two things? For A and B, what does it have on yours? That slash, that straight up and down line. Do you remember what that means? Conditional, given that. I know that this happened. I know that event B took place. We wrote down a rule for this the other day. The probability of A, if I already know that B happened, is the same thing as the probability of A and B, the intersection, divided by the probability of just B. Do we have this information? I know the probability of A and B. No. Do I have this information? Yes. What about this? So can I find the probability of the intersection? Yes. We need the intersection if we're going to test for independence, because I need that to compare it to the product of A and B together. All right, so we're going to have to find our intersection over here. What would I put in for this side right here? 27 over 50 is equal to the probability of A and B, which is the thing that I really want, over what? 1/2. Fractions mean what operation? Division. How do I undo division? With multiplication. So I'm going to multiply by 1/2 because I'm dividing by 1/2. And if you do it to one side, you have to do it to the other side. So my 1/2s will cancel each other out. That means I'm going to have the probability of A and B all by itself over here. And then I multiply fractions how? Straight across. So I end up with 27 over 100. Now I have that important piece of information that I can substitute in over here in my test. 27 over 100. What's the probability of A all by itself? 9 over 20. We're going to multiply that to the probability of B, which we said was what? 1 over 2. And I'm going to multiply these fractions straight across. So I end up with what? 9 over 40. Well, if they don't have the same denominator, it's really hard for me to compare these fractions. Or if they don't have the same numerator. So why don't we pop these into our calculators and we'll compare the decimals. Do 27 over 100 first in your calculator. What is this in its decimal form? 0.27. Now let's do 9 divided by 40 and we'll write it down in its decimal form. You said 200 what? So 225? Are those equal? No. So what does that mean? If they're not equal, then they are not independent. And if you are not independent, is there a relationship or not? There is a relationship. All right. Flip the page for me. There's one more thing I want to look at with you guys. We have Hank. Hank plays baseball. Hank is getting ready to go up against a left-handed pitcher. And he wants to know whether or not he's got a better chance of a home run with a left-handed pitcher than with a right-handed pitcher. So he's got his stats recorded here. The chance of getting a home run if he's got a left-handed pitcher is 30%. The chance of hitting a home run if he has a right-handed pitcher is 11%. The chance of getting a home run overall is 15%. and the chance that he gets a left-handed pitcher in the league that he plays in is 20%. I'm going to draw a tree diagram here. Anybody ever swung a bat at a baseball before?
Yeah.
What's the first thing you would know, whether or not you get a home run or whether the pitcher is left or right-handed?
The sound of the metal through the baseball bat.
So which thing would you know first? Yeah, you're going to know first whether the pitcher is left-handed or right-handed. So that's what I'm going to put first on this tree. We've got left-handed pitchers and we have right-handed pitchers. What's the chance in this league that somebody is a left-handed pitcher?
30%.
I don't want to know about home runs yet, just whether or not somebody's a left-handed pitcher. Yeah, 0.2. 20% chance somebody is a left-handed pitcher. So 0.20 or 20%. So what percentage of pitchers in this league are right-handed then? 80%. All right. So Hank gets a left-handed pitcher, and one of two things happens. He either does hit a home run or he doesn't. If he got that left-handed pitcher, what's the chance that he hit a home run? 30%. That's this piece right here. So if he got a left-handed pitcher, there's a 30% chance that he hit himself a home run. What's the chance he didn't hit a home run then? 70%. Okay, Hank is standing in front of a right-handed pitcher. One of two things happens again. He either hits a home run or he doesn't. If he got a right-handed pitcher, what's the chance that he hit a home run? 11%. So what's the chance he didn't hit a home run? 89%. I want to calculate the probability that Hank got a left-handed pitcher and hit a home run. 0.06. Right-handed pitcher and hit a home run. 0.088. Are his chances the same with both types of pitchers? No. So is there a relationship here? Is one thing influencing the other? Or are the chances the same regardless? Chances are not the same regardless, so there is a relationship here. These are not independent events. If he had the same chance of a home run, no matter what kind of pitcher he got, then those events have no relationship and they would be independent. Have a great rest of your day, guys. I'll see you tomorrow. Or Monday, not tomorrow.